In 2.1, we talk about the slope of the tangent at this point P is the limit of the slope of the secant line PQ as you move the Q along the curve closer and closer to P. And the instantaneous velocity of an object is the limit of the average velocity of the object as you make the time interval closer and closer to 0. Suppose we have an object move along a straight line. The position function is given to be f of t. Then the average velocity of this object is given to be the displacement divided by the time elapsed. Displacement is equal to the final position subtracting the initial position here. So that will be f of a plus h, subtract f of a. And the time passed over here, from time t equal to a to the time t equal to a plus h, the time passed here is h. So the time elapsed here is h, divided by h. So instantaneous velocity at a is the limit of f of a plus h minus f of a over h as h approaching 0. What is formula 3? This is the formula for instantaneous velocity. If this curve here is the curve for a position function f, then the instantaneous velocity at a is equal to the slope for the tangent line when x equal to a right here. So the slope for the tangent and instantaneous velocity, they are equal. Okay. As you recall this from section 2.1, the instantaneous velocity at a and the slope of the tangent when x equal to a, these two are equal to each other. Now we call this problem here in section 2.1. So this is an observation deck right here. And from here to the ground is 450 meters. The position function of a ball that is dropped from this observation deck is given to be ft equal to 4.9 t squared. We need to find the instantaneous velocity at 5 seconds. Now, to find the instantaneous velocity at 5 seconds, how about we find the instantaneous velocity at any time a? Then later we can substitute a to be 5 or a to be 6, a to be 9, etc. So instantaneous velocity according to formula 3 above is the limit of f of a plus h minus f of a over h. Here h approaching to 0. Now f of a plus h is 4.9 times a plus h squared. So you just substitute a plus h into t. And now you substitute this a into t. You get 4.9 times a squared. Now divide by h. Over here, you can take out this common factor 4.9, and then we can use the difference of 2 square formula to factor this a plus h squared minus a squared. So that's the difference of 2 square formula. So you got a plus h plus a times a plus h minus a, and 4.9, you just carry that down. Now notice that a plus h minus a is equal to h. So that will cancel out. And this part here simplified into 4.9 times 2a plus h. Now we can do a direct substitution. Substitute h to be 0 here. We got 4.9 times 2a, which is 9.8a. So this gives us the instantaneous velocity at any time a. Now we can substitute different time, different a into this. So at 5 seconds, substitute 5, we got 49. The unit here is meter per second. At 9.6 seconds, that will be 9.8 times 9.6, which is about 94 meter per second. So we can substitute different a into this to find instantaneous velocity at different moments. Part B. How fast is the ball traveling when it hits the ground? This is a position function. If we know the time that it hit, now over here when they say how fast, which means they're trying to find the velocity, the instantaneous velocity, okay? So if we know the time, we can substitute the time into this A, then we can calculate the instantaneous velocity. But we don't know the time yet. Okay, but we can find out the time by using this information. So we want to find what is the time that the ball hits the ground. So this is a position function. So when you hit the ground, the position here will be 450 meters. Now substitute 450 into f of t because that's the position. We solve for t here. So t squared will be 450 divided by 4.9. Now we can take the square root. So we only consider the positive square root because the time here we only consider positive time. So do the calculation. This is about 9.6 seconds. Now we can substitute 9.6 into A, and we found the instantaneous velocity at 9.6 seconds is about 94 meters per second. So when it hits the ground, the velocity is about 94 meters per second. Now notice that we have three formulas so far. These two give you the slope for the tangent line at P. This one gives you the instantaneous velocity at the moment A. Okay, notice that limit of this form arises whenever we calculate a rate of change in any of the science or engineering, such as a rate of reaction in chemistry or a marginal cost in economics. So we want to give a special name to limit of this form, okay? So we call them the derivative of the function f at A. And it is written as f prime of A. So this symbol here, we read it as prime, f prime of A. As you see, f prime of A could represent m, which is the slope of tangent, could be the instantaneous velocity VA, could be other instantaneous rate of change of the function y equal to f of x with respect to x when x equal to A. Notice that v of A here represents the instantaneous velocity at time t equal to A. So for the speed of the object at time t equal to A, now speed, we only consider the magnitude of that. So we don't consider the direction. So speed is the absolute value of the velocity. So that we're going to put an absolute value over here. That will be the speed of the object at this time t equal to A. Example, find the derivative of the function f of x equal to x squared minus 8x plus 9 at the number A. Now, the derivative of the function f of x at A is f prime of A. By the definition, it's the limit of f of A plus h minus f of A over h plus h approaching itself. F of A plus h, we substitute A plus h into x over here, we got this. Substitute A into x over here, we got this. Now divide by h. We can expand this perfect square here. Then you see that this a squared minus a squared going to be canceled out. So leaving you with 2ah plus h squared. This also cancel, this cancel, and then minus 8h over h over here. Everything in the numerator going to divide by h. That would simplify into this. Now over here, the A here is a temporary constant. H is changing. So substitute H to be 0 here. You get 2A minus 8. So the derivative of the function at A is 2A minus 8. Now we try to find an equation of the tangent line to this parabola at this point 3, negative 6. First, let's do a quick check to see if this point is on this curve. Substitute the x and y into this equation. Notice the left side equal right side. So yes, indeed, this point is on the curve. Second, we need the slope of the tangent in order to write the equation of the tangent line. So the slope of the tangent, remember, is equal to the derivative of the function at this A, which is 3. So that's equal to f prime of 3. Well, we just calculate f prime of A is equal to 2A minus 8. So we're going to substitute 3 into this A. So that will be equal to 2 times 3 minus 8, which is going to equal to negative 2. Once you get the slope, then you can use the point slope form to write the equation of the tangent. So it will be y minus negative 6 equal to negative 2 times x minus 3. Isolate this y, we got y equal to negative 2x. So this is equation of the tangent line in slope-intercept form. So the derivative of the function at A represent instantaneous rate of change. For example, in graph, they can represent the slope of the tangent at A. In physics, they represent instantaneous velocity at time A. And in chemistry, it can represent rate of reaction. In biology, it's rate of change of the population of a colony of bacteria with respect to time. In economics, it could be the marginal cost, which is the rate of change of production cost with respect to the number of items produced.